Okay. On Wednesday, we applied the continuity equations to the problems of the water tank, and then we have additional exercise. Still, the tank, but we focus on the fluid material is the gas. So as we can see, what's the questions? We have the small hole, and the small hole with the area is the is the 10 minus 7 powers meter square, and the total volume of the tank is the 10 meter cubic, and the methane escapes so slowly that the temperature in the tank remained constant at the 23 degree. So we have the temperature, we convert to the unit degree to the Kelvin. So here is the 273 plus the 23 degree. So that will be the 296 Kelvin. And the mass flow rate of the methane through the hole is given by the m dot is equal to 0.66, the pressure, and then multiply the areas of the hole divided the root gas constant multiplied the absolute temperature. So as we know, the pressure in equations is the P is the pressure in the tank, and the area of the hole we use the A, and this is a gas content. Okay, T is temperature. So what's the problem? We need to calculate the time required for the absolute pressure in the tank to decrease from the 500 kilopar to be the 400 kilopar. Okay, so that's our questions. So for these questions, we can certainly define the control volume, just the inside, right? And the dictionary showing here is our control service. So for these questions, we only have the mass flow rate associated with the outflow. So we only have the outflow, and we don't have any inflow rate. And the mass included in control volumes will be changed with the time difference. Okay, so for these questions, we only need to focus on the mass in control volumes change with the time, and we only have the one the mass flow rate for outside for output, so that will equal 0. Okay, so we start from the discuss with the MCV will equal to the M, the shell. This is the tank. We have the shell, the mass included in the control volumes, and we know that the mass of the massive gas in the tank will equal to the density multiply the total volume. Okay, and then we compute the differential of the MCV dt will equal to the dm shell and the dt, and here will equal to the d rho dt, and keep the total volumes and then plus the rho is fixed, and we use the total volumes dt. Okay, so we can check the items each in the formulas. With the mass shells cannot change with the time, and the tank of the volume also fixed, so we don't have this item. So you can rearrange the final terms. We have a total volumes and multiply the density change with the time. Okay, and based on the ideal gas law, you know that the density of the gas will equal to the pressures divided the gas constant and divided the absolute temperatures. Okay, so based on the two equations showing here, you can rewrite the dmCV change with the time will equal to the total volume and the dt, the inside of the density replaced by the ideal gas law. So the inside is the pressure divided RT. And we know that the RT are the constants parameter. And so we can take outside, didn't change with the time. And the inside we only have the pressure dP and dt. Okay, so we can go back to the continuity equation in here. So our formula is the total volume divided RT and the dP dt plus the outflow rate showing here, right? So we just put the formula 0.66 pressure and the total area divided RT is equal 0. Okay, so we know that the total volume divided RT and the dP dt equal to the minus 0.66, the total area divided RT and multiply the P. So we put the pressure together. Okay, so that's the dP divided the P, and the right hand side we combine all of the constant value together, so we have a total area and divided the total volumes, and the RT divided the root RT will equal to the root RT in here. Okay, and we have the dt. So go back to see the questions, we need to answer the time required for the absolute pressure in the tank to decrease from the 500 kilopascal to the 400 kilopascal. So right now we can do the integration, and we know that the pressure will start from the 5 kilopascal to be the 400 kilopascal. So 500 kilopascal to 400 kilopascal, and at the time we don't know. Start from the 0 to the time final is required. Okay, so we can put all of the values inside the formula right now. So the minus 0.66, and the area is the 10 minus 7, and the total volume here is the 10 meter cubic, and the root inside we have the gas constant value in here. Okay, in here is a 518, and the absolute temperature is 296. Okay, and there will to the D final is TF. So I compute the constant value in here, use my calculator, and then you can check from your calculator. Okay, so take the root for the RT and multiply the 0.66. Okay, and so that will equal to the minus 258.43 10 minus 8 powers TF. Okay, and the left hand side, the item for the pressure, we do the integration, so we know that will equal to the rho and P and the domain interval is 500 kilopar to the 400 kilopar. Okay, so that will equal to the rho 400 kilopar divided 500 kilopar, and will equal to the minus 258.43 10 minus 8 powers and TF. So we can compute the how large of the TF in this formula. So again, I use my calculator to check the answers. Okay, so and divided the 258.43 and then multiply the 10 8 powers. So the TF will equal to the 8 4 6 3 4 6 around seconds. Okay, so this is almost equal to the 1 day. This is almost equal to the 1 day times to estimate the masses, and the pressure inside the tank will start from the 500 kilopar to the 400 kilopar. Okay, so this is the questions. Usually we apply the continuity equation to understand how many times required for the pressure change in the tank. Okay, so we move to the next. The next we still discuss with the continuity equation, but the condition is the water, the fluid flow in the conduit. Okay, so as you can see in the conduit conditions, we have there is the inflow and then there is the outflow. So we have the inflow in here, and there is the outflow. And the dashed line showing here is our control surface. And because we are always in the fluid flow always in the conduit for the control volumes, the mass didn't change in the control volume. So you can rewrite the continuity equation. We can say that we have the integrations in the control volumes, the density multiply the total, multiply the small volumes, and the change with the time plus we do the integration along the control surface, but the inside is a row v factors dot product with the small piece area factor will equal to 0. But in the conduit, as I said before, we don't the mass in control volumes didn't change with the time, so we don't have this item. Okay, so the continuity, finally we only have the integration along the surface, and we have a row v factors, dA factors, and will equal 0. Okay, and then we can also expand the integration part. So the outflow row v factor dot product with the small peak area factors minus the inflow will equal 0, right? So this is the continuity equation for the flow in a conduit. Okay, and then we can also assume the velocity is the uniform flow, and the flow velocity factors is always parallel to a normal factor of the cross-section area. So you can rewrite the integration formula to be this formula. So we have a row 1 density multiply the cross-section area 1 multiply the velocity 1 will equal to a row 2A2V2. Okay, so this is also the for the pipe flow form of the continuity equations. So but above we think the integration along the control volumes, the row dV and the dt is always equal to 0, is especially for the steady flow. But in the unsteady flow, it's unsteady state flow, you cannot say the mass accumulation is always equal to 0. So that will maybe non-zero or unsteady flow for some unsteady flow problem. Okay, so you can keep in mind. Right now we say that the continuity equation in here only for the steady flow. Okay, so we have some very quick exercise to help us better understand how can we apply the continuity equation to the pipe flow problems. So as you can see, we have the cross section in here, the cross section 1, and that's the cross section 2. And we know that the left hand side is our inflow part, and the section 2 is our outflow part. And the question requires we to answer what is the water speed in the section 2. So that means we didn't know the V2, right? The V2 is our unknown parameter in these questions. So because this is the pipe flow, so we simply apply the continuity equation for the pipe flow problems. So we have a constant density, and we have the cross-section area A1, and the velocity V1 will equal to the constant density A2 and the V2. So because the unknown parameter is the V2, so I keep in the V2 in the left hand side, and we know that that will equal to the A1 divided the A2 and multiply the V1. Okay, then because this is the pipe, so we know that the cross-section area is 4 over pi d squared. So in here, the cross-section area ratio can be rewritten by diameter 1 divided the diameter 2 and the square and multiply the V1. So we go back to see the questions. The D1 diameter is equal to the 1.2 meter, and the D2 is 0.6 meters, and we take the square, and the V1 velocity showing here is 2 meters per second. So we know that the final in here will equal to the 4 times multiplied 2 meters per second. So the final is 8 meters per second. Okay, so the question is quite simple. You just determine the velocity, flow velocity for the different cross-section areas, and based on the continuity equation ideas. Okay, so this is another exercise. We know that the water with the density, okay, the water with the density is the 1,000 kilogram per meter cubic, and the flow through a vertical Ventory meters as shown. And a gauge pressure, a pressure gauge is connected to close to pipe, okay, and it can measure the pressure difference between the section 1 and the section 2. And we know that the section 1 area is A1 and there is the A2. So we know that the area ratio for the A2 divided the A1 is equal to the 0.5. Okay, and the velocity in the pipe is the 10 meter per second. So we know that the V1 is the 10 meter per second. So please find the pressure difference recorded by the pressure gauge, and assume the flow has the uniform velocity distribution, and that viscosity effects are not important. So first, we can apply the continuity equations to calculate how large velocity located on the cross-section area 2. Okay, so again we have the low and the A1 V1 will equal to the low A2 V2, right? But now we didn't know the V2, so we keep the V2, and all of the parameter move to the right hand side. So the A1 divided the A2 multiply the V1. As we have the ratio in here, so we can quickly calculate how large the V2. So the A1 and divided the A2, where the ratio is equal to 2, and the velocity in here is the 10 meter per second. So we know that the V2 velocity is 20 meter per second. Okay, so that we first apply the continuity equation to understand how large flow velocity at the cross-section area 2. And then the second, we can apply the Bernoulli equations. Okay, so we can apply the Bernoulli equations So we can write down the Bernoulli equation. Government equation is the we have the piezometric pressure. We have the piezometric pressure at the location 1 plus the 2 over rho V1 square will equal to the piezometric pressure 2 multiply plus the 2 over rho V2 square. Okay, so we know that the piezometric pressure difference 1 minus the piezometric pressure difference 2, and so the pressure difference will equal to the 2 over rho V2 square minus the V1 square. Okay, and then we know that the density in here is the 1000 kilogram per meter cubic, and the inside is the velocity is 20 square minus the 10 square, and there will the meter square divided second square. Okay, so you can use the your calculator to double check the answer showing here. So the 20 square minus the 10 square, and the multiply the low density divided the 2. Okay, so the answer is equal to the 150 and the kilo per. So that is our final answers. So for these questions, very important is usually we will combine the continuity equation and the Bernoulli equation to understand the velocity flow or the pressure changes along the pipe. Okay, so don't forget the Bernoulli equations as you have learned in the previous chapters. Okay, so that's we go back because we know that the continuity equations and the continuity equation for the pipe flow, we actually know the A1 V1 will equal to the A2 V2. So we know that if we have the small cross-section area, we'll have the larger velocity. Okay, and the larger velocity based on the Bernoulli equation, we know that the larger velocity will have the lower pressure. Okay, the larger velocity will have the lower pressure. So what's the problem? We go back to see the cavitation problem. So as you can see here, if we our environment the pressure will decrease, and then the phase of the fluid will from the liquid to be the vapor. So what's the problem for the vapor? So previous we have known that, for example, the cavitation problem will degrade the material because of the higher pressure associated with the collapse of the vapor bubble. So that indicates when the vapor bubbles collapse will generate very high pressures, and we call that the very high pressure is intermittent pressures, and the values can reach the 800 MPa. So it's very terrible pressures compared to the environment pressure. And the sentence just show we know that the fluid for the water and the vapor pressure at the 15 degrees is the 1.7 kilopar absolute. So usually to avoid the cavitation, the designer can configure the system so that the pressure at all locations are above these PV values. So if your environment pressure is smaller than the vapor pressure, will have the cavitation phenomena occurred. Okay, so what's the problem? As you can see, the vent, the surface will broken by the vapor bubbles. Okay, and the sun destroys surface also caused by the cavitation phenomena. But the cavitation is not always terrible, because we can apply its properties for some useful purpose. That's the super cavitations torpedoes have been developed. It's based on the idea if we have a large cavitation on the surface of the torpedoes, and then can significantly reducing the contact area. So that's why the torpedoes can move very faster. Okay, and also the cavitation can be applied to destruct the kidney stone. Okay, so not always terrible, also have some useful applications if you can design the very useful for a cavitation problem. Okay, so but for the real cases, usually we would like to understand where the location can have the cavitation phenomena. So we need to predict the cavitation. So, and the cavitation, the key knowledge is where the location with the lower pressure. So sometimes the elevation increase, the pressure also decrease, and some location with the higher velocity based on the Bernoulli equation, you know that the high velocity will result in the lower pressure. And some sections side of the bump also will have the lower pressures. Okay, so you can design the different conditions. As you can see, if the slow velocities, the dash line cannot touch to the vapor pressure. But if you change your flow velocity to be the higher and the faster ones, so in that the cross-section area, in that small cross-section area, your pressure will touch the vapor pressure line, and then you will have the cavitation phenomena. Okay, so the most important thing is how can we predict the cavitation problems. So this is another cartoon figure we show if only the small slower velocity, you can also only see some vapor bubbles. And if your velocity is quite higher, and you not only have the vapor bubble, you have the vapor pocket. Okay, you have the vapor pocket. It's more terrible phenomena. Okay, so the exercise we are trying to predict where the location with the cavitation phenomena. Okay, so the questions tell us we have this sphere, the circles in here, and what is moving in the water with a certain depth where the absolute pressure is the 18 psia. So that indicates we have I plotted the straight line in here. Okay, and then we know that the point in here the vapor, the absolute pressure. Maybe I use this is the P0 will equal to the 18 the PSI absolute pressures, and then the maximum velocity on the sphere occurs on 90 degrees from the forward stagnation point. Forward stagnation point for the 90 degrees, so the point move to here is the 1.5 times of for the free stream velocity. So the free stream velocity in here is the U0, and the velocity in here we may use the U1 is 1.5 times of the U0. And we know that the density rho is equal to the 62.4 bound mass divided Ft cubed. So please calculate the speed of the sphere at which cavitation will occur. Okay, so we actually know the cavitation will occur. So we in here maybe the pressure will equal to the vapor pressure at these temperature conditions is equal to 0.178 psia. So we need to calculate how large U0 in this condition, and we will see the cavitation occurred. Okay, so the first we need to apply the Bernoulli equation. Okay, so we know that the Bernoulli equation tells us the P0 pressures multiplied plus the gamma Z0 and plus the 2 over rho U0 squared will equal to the P1 and plus the gamma Z1 and plus the 2 over rho U1 squared. Okay, and for these questions we assume the sphere is quite smaller enough, so we think the elevation difference from the Z0 to the Z1 is quite smaller. Okay, so we just cancel out the gamma Z items, and we know that the P0 minus the P1 will equal to the 2 over rho and the U1 square minus the U0 square, right? And we actually know the pressures. The P0 is the 8 psia and minus the 0.178 psia. Okay, will equal to the 2 over rho in here is the 62.4, and the unit is the bound mass divided the Ft cubed. Okay, 2 over rho, and the inside is the U1 is the 1.U0, right? And the U1 square, so here is a 1.5 square U0 square minus the U0 square. And the unit in here we use the Ft divided the second, and the Ft square second square. Okay, so now we need to take a care how about the unit for the PSI. So we know that the PSI 1 psi is equal to the 1 pound force divided the inch square. Okay, divided the inch square, and then we know that the 1 inch 1 ft will equal to the 12 inch. So in here we know that we can convert the inch square to the ft square, so that will to be a 144. Okay, 144, and the pound force to be the ft square. And then we also know that the 1 pound force will equal to the 32.17 pound mass multiplied the ft divided the second square. So we just also multiply the 144 multiplied to the 32.17, and the unit will to be the pound mass, and divided f t square, and multiply the ft divided the second square. Okay, that will equal to, I use my calculator to check the answer in here. So that will equal to the 463.2.48, the pound mass divided the ft divided the second square. Okay, so we can put the numbers go back to here. So we have the 8 minus the 0.178, 18 multiplied 0.178, we change the psi to be the pound mass divided ft and the second square. So here we multiply the 4632.48. So the unit is the pound mass divided the ft divided the second square, will equal to the same unit, the right hand side with the same unit. Okay, and I use the calculator to compute the number shown here. 1.5 multiplied 1.5. So the 1.5 square minus 1, and divided multiply the density 62.4 divided the 2. So here is equal to the 39, and we have a u0 square. So we just take the u square in the left hand side and compute all of the number we have. So the 18 minus the 0.178 multiply the 4632.48 divided the 39. Okay, so the u0 square will equal to the 2116.9. So you can calculate the root values of the u0s. So that will equal to the 46 ft per second. Okay, so that's you can compute the velocity for the severe will have the 46. If your velocity speed higher than 46, you will have the cavitation phenomena. So for the engineering designer, we cannot have the higher speed higher than the U0 showing here for these questions. So that is very important exercise. How can we predict the cavitation problem? Okay, so the next semester we have the fluid laboratory experiment related to the Ventory tube. So as you can see, you have the Ventory pipe in here. So I change the color pen. So you have the pipe, and actually the pipe showing here have a different cross-section area. As you can see the cartoon figure showing here, we have a different cross-section area, and the different cross-section area connect with the pressure gauge. Connect to the pressure gauge. So the here is the pressure gauge. We have the pressure gauge in here. Okay, so the bottom, the red square in here is the Ventory tube, and the upper in here is our pressure gauge. So we just based on the idea. First one is the continuity. So we know that for the continuity equations, okay, for the continuity equation, we know that the A1 V1 will equal to the A2 V2 will equal to the blah blah blah. Okay, it's a S3 V3. So based on the different cross-section area, we can convert the velocity for a different cross-section area. And then the Bernoulli equation tells us the piezometric pressures plus the 2 over rho V1 square will equal to the piezometric pressure 2 plus the 2 over rho V2 square. So we can, because we already have the velocity at a different cross-section area, and then we put the information inside to the Bernoulli equation, and then we know that the pressure difference. Okay, so we based on the two equations to compute the pressure difference. So we have the pressure difference, and this is we call the theoretical pressures. But also you can say that is the predict pressures. But for the pressure gauge in here, we already have the observed pressures. Okay, so this experiment we are going to compare two pressure values. One is for the predict, another is observe. So we have the predict and the observe pressures, theoretical and the observed pressures. We can compare their difference. We can compare for their difference. So actually they will have some difference between the theoretical and the observed, because previous chapter we discussed with the Bernoulli equation, we didn't consider the viscous effect, but sometimes our practical situation will include the viscous effect. The viscous effect will have some energy passitations. Okay, so we call that the difference related to the header rows. And in the following class, we will discuss with the header rows. But in here, for this laboratory experiment, we are trying to discuss with the header rows. But you have the continuity equations and the Bernoulli equation, you can predict the pressure. And we call that the theoretical pressure. and then you can compare with the observed pressure, and then you can discuss how large difference they are. Okay, so that's the Ventory experiment in the next semesters. So the next one we will briefly introduce to the differential form of the continuity. So we may start here, and we have the 10-minute breaks, and after break we'll come back to the class. Okay.